Today we're talking about acids, not the stuff that you drop. None of that. I know it was on your mind. Okay.
Well, I'll make it going. It was nice. Well, I didn't really see anybody, but it was nice seeing you guys. I'll hopefully see you guys later. Yeah. Bye.
Okay. Can you guys see? Can you see the lecture? Is it showing? Yeah.
Yeah, I could see it.
Okay. Good. Okay, so today we're going to be talking mainly about acid and bases. You guys, we kind of introduced it, but we're going to give you guys a little bit more, right? Because when you're dealing, as Haley pointed out, when dealing with organic chemistry, you deal a lot with whether something is going to be an acid or a base and how it's going to behave, okay? Okay, so when we talk about an acid, we always talk about an acid as being a proton donor, right? So acids loses a proton. Bases are going to gain a proton. So right here, this guy, HCl, is an acid. It's going to be losing its proton. It's going to donate it to the water. Okay, so when it donates to the water, this guy becomes our conjugate acid. This guy becomes, this guy becomes our conjugate base. This guy becomes our conjugate acid. Okay. So now the thing about acid and base reactions, most acid and base reactions are reversible. Do you guys know what I mean by reversible? It can go either way. Yes, it can go either way. Now, this here is a strong acid, right? So it's going to be favoring one direction more so than the other. But technically, it still can go back the other direction, right? Under the right circumstances, we can drive it to the other direction, okay? And you guys remember Le Chatelier's principle? Like when you have, let's say we remove all of the chloride ion out of the system, which way is that going to drive the reaction? So if I take this out, if I start just pumping this guy out, which way is that going to drive the reaction? It's going to drive it, yes, it's going to drive it towards the dissociation, right? So if I put more in, right, then it's going to drive it the other way, right? Okay, so this is just basically saying what I just said. Most reactions are going to be reversible. This here is an example of a irreversible reactions. There are irreversible reactions. They're often limited by the entropy of the system, which we didn't talk a lot about in our previous class. We kind of touched on just barely, and that's kind of like the order, whether there's order or whether there's chaos. Okay, so we talked about the conjugate, right? So here, this is the acid, this is the conjugate base. This is the base in this case, and this is our conjugate acid, okay? So when the proton is donated to the water then becomes an acid, right? So that hydronium ion makes it an acid, right? You guys remember this is called the hydronium ion? Let me spell it for you. I know it's like, God, you're talking all this stuff that we already know. We know this like the back of our hands, right? Hydronium. Okay, so this is the hydronium ion. And you remember how that works, right? It basically, you got that H plus, it attaches to the water, it says, oh, I love you, I love you, I love you, I'm not gonna let you go. And it does that until it finds something else it can attach, right? Okay. Watch on the exam, you're gonna have a question. I love you, I love you. I'm joking. Okay, so in the case of ammonia, we have ammonia in water, right? So ammonia, in this case, is going to be a base, and the water is going to act as an acid. Now, this is the beauty of water. Water is kind of like it's right there in the middle, right? So under one circumstance, it can act like a base. On another circumstance, it can act like an acid. Man, water, you know? such a player, swings both ways in so many ways, right? So there interacts with, remember, with the sodium and the chlorine. It's like, hey, baby, and then it goes to the other, hey, baby. So it does the same thing in this context, right? It's able to be a base and an acid depending on the context that we need it. So in this case, we're removing one H plus, right? So then that H plus forms, what is this ion called?
Ammonium.
Although my minus is in the wrong spot. So it's the ammonium ion, right? You guys remember that, right? Polyatomic ion table, right? So that's ammonium. This is ammonia. They're different, right? My plus is in the wrong spot. I apologize. So in this case, now we've taken that plus, right, that H plus, and we've added it to the ammonia. And so then we're left with the hydroxide, right? So that's the hydroxide ion. And who it's working with, right? So, it's kind of like, kind of like us, right? So sometimes we're the cool kid, sometimes we're the follower, right? Sometimes we're the leader, sometimes we're the follower, right? So this group, I'm the leader, right? And then my other group, I'm the follower, right? So it just depends on who I'm with, right? So that's the way water kind of works. It depends on who it's with, okay? Okay, so, yes. Well, if it's reacting with an acid, what is it going to be? It's going to be a base, right? If it's reacting with a base, then it's going to be an acid. Doesn't that make sense? Yeah. Okay. Yeah. Good question. Yes. You're putting the dots together. Okay. Okay, so the stronger the acid, the weaker its conjugate base is going to be. Okay, and that kind of makes sense. If you have a really strong acid, you're going to have a weak conjugate base, right? Okay, acids are going to have different strengths, right? So we're going to have strong acids and we're going to have weak acids. Can you guys remind me? We've talked about these guys. So tell me some strong acids. Halogens, yes, except for one. There's one that's weak. One of the halogenic acids are weak. Idonic, yes. Okay. Hydrofluoric. Hydrofluoric is the weak one. All right, do you guys remember why? It doesn't want to let go. Remember, hydrogen is a bully. Calcium is a bully. That's right. Calcium is a bully. He's like, no, you're not going to let go. I'm going to keep you. And so that's weak acid, right? And we know that if it doesn't dissociate, that H doesn't get removed, that is what makes it weak. Okay, so give me another example of weak acids that we know for sure that are going to be weak acids.
Carbonic acids.
Carbonic acid. Carbonic acid is a weak acid. Why is carbonic acid a weak acid? Because it has carbon. That's right. Carbon acids are going to be weak acids. Okay, so basically, in the case of weak acids, we're going to be favoring staying together rather than moving apart. So you're going to be favoring, in this case, the reactants. In the case of acetic acid, which is a carbon acid, right? So this guy is favored. So you're going to have more of this guy in solution than you're going to have these, okay? But in a strong acid, in a strong acid, you're going to have more of the ionic forms right? The separated form, the dissociated form, than the form that's together. So you're gonna have very little of this, but you have tons and tons of this, right? You guys remember that? Because it dissociates. It almost dissociates completely, right? And that's what this arrow basically shows us. If the arrow is long going in that direction, that basically means it's favoring the products, right? Or the dissociation. If the arrow is long going in the other direction, then that means it's favoring the reactants. This way. Gosh, it's not working. Yeah, this way. Oh, there's new stuff. Ooh, let me see if this works. Oh, cool. Okay. Yes, yes, yes. On a test, the size of the arrow matters. Yes. Did you say great? Don't get smart now. I mean, no, get smart now. Okay. So, and we already know that, okay, so when we say that, right? So it favors the products, okay? Now, we know that there's a point where we reach our equilibrium, right? And in the case of strong acids, the equilibrium is favoring the products. That means that the products are going to be much more abundant than the reactants in the strong acid. And it's going to be just the opposite in a weak acid, okay? And what does that mean, right? Equilibrium. God damn it, what was that? Equilibrium? You guys remember how to determine the equilibrium constant? Let's say we're doing it for hydrochloric acid. How would we figure out the equilibrium constant for hydrochloric acid? And let's put everything the way it should be. Yeah, this is AQ. This is L, which is dumb that we even do it. This is AQ. And this is AQ. Okay, so how would I determine my equilibrium constant, KEQ? It's going to be my products over the reactants. But am I going to take everything in consideration? Is everything created equally? No. What am I not going to take in consideration? The water. So based upon this, if we're at equilibrium, we're going to have much more of this guy than this guy. So then our KEQ is going to be greater. This here is also going to be called our Ka for hydrochloric acid. Ka stands for acid. The A stands for acid, right? Okay. What's that? It's been a while. It's a little rusty. We're shaking off those, yes, those cobwebs. Okay. Okay, so we know that that's what it boils down to. That's what our equilibrium constant is going to be. Okay, what is another thing that we don't take in consideration? Do we take gases into consideration? No, it's incorrect. Well, we don't take solids into consideration, but we do take gases into consideration. So we'll take gases in consideration and we'll take aqueous solutions into consideration. That's pretty much for everything. Although you're going to see, hold on, it gets a little more complicated. Okay. No, no, you don't take liquids and solids into consideration. Yeah. Oh, yeah, that's what I'm saying. Yeah. I thought you're saying liquid and solids we take into consideration. No. So you're taking gases and aqueous solutions into consideration. And that's also in terms of kinetics, right? You guys remember that? Oh, we got to brush out those cobwebs. Okay. So here, this is just the equation, but we know that that concentration of water, we're not going to take in consideration. It's just going to be left down to this equation. Okay. And this is the generic form of our equation. Okay. There's a lot of things missing on this. I need to fix this slide completely. Hot mess slide. Okay. Okay, so then if we look at this, now if it's a strong acid, that means our Ka value is going to be big, right? So not our pKa, we're talking about our Ka value, okay? So pKa is represented as minus the log of Ka, right? So if we go back, let's go back to our equation here, right? So we're neglecting this part here. Okay, so if it's a strong acid, the upper part is going to be more abundant. You're going to have a higher concentration of your hydronium ion and your base compared to the acid as a whole, right? If it's a weak acid, then you're going to have higher concentration of this guy compared to this guy, right? So if we have a higher concentration up top over the bottom, is that value going to be a high value or is it going to be a low value? It's going to be a big value, right? And then if we have a higher concentration at the bottom rather than the top, then that's going to be, okay? So does that make sense? Right? So then when we talk about the log of it, right? So now we're saying we're taking the minus log. It could get there. So minus log of our pKa, right? So if it's less than 1, that means it's a strong acid. That basically means that our Ka is really big, and this guy makes it a minus, so it's going to be a really small value, right? It's going to be less than 1, right? If it's from 1 to 3, if our pKa is from 1 to 3, it's a moderate strong acid. If our pKa is from 3 to 5, it is a weak acid. If it's from minus 5 to 15, then it is a very weak acid, right? Okay. Does that make sense? I would know it. I mean, it helps you figure things out faster, right? You don't have to, you don't memorize anything, right? I mean, you may want to, yeah. So, but it helps in the long run. And it's going to be important for us to understand how things are going to behave, whether it's going to be a strong acid or if it's going to be a weak acid, right? Because strong acids are going to have almost instantaneous effects, where weak acids, they're going to take a while to happen, right? Okay, so the larger the acid, the larger the pKa, right? I'm sorry, the stronger the acid. The stronger the acid, the larger the pKa. The stronger the acid, that's wrong. The Ka, sorry, I typed another typo, sorry, my bad. Smaller, I should be smaller. Yeah, see, I'm just testing your skills. The smaller the pKa, okay? The stronger the acid, the smaller the pKa. Did everybody make that correction? So hopefully everybody's here so that. Yeah, that is a nice way of looking at it, yes. Okay, so let's see. Oops. So we know the pH scale. Sorry, so many things are going through my head right now. So this kind of gives us an idea. of how things are. So let me clear. Okay, so pH is determined by minus the log of the concentration of the hydronium ion, or just the H+ ion. Okay, so in this case, this kind of lets us know our nice little scale here. So water should be around neutral, right? So milk is that a strong acid or a weak acid based upon this scale?
Weak acid.
Or is it an acid? Are you sure? Where is it located at? It's a weak acid. It is a very, very weak acid. We also know that milk has, guess what in it? What does it have in it? It has lactic acid, which is a very weak acid. It's a carbon acid. Okay, then we know, let's see, saliva. Saliva is weak. Rain is weak. Why do you think rain is acidic? It does have acid in there. So it's acidic rain. Yes, we know it's acidic. Why is it acidic? Because of the carbon dioxide, right? So because of carbon dioxide that's in water, because the environment that we live in, we're kind of polluters and everything like that, we make our rain more acidic than what it should be, right? So now rain has an acidic, so it's around 6, what is that, 5.9 or something like that, right? So coffee that you have in the morning, this is why I have such burn, is because I love coffee and my coffee is acidic. Tomatoes, oh, it's like pasta. God, I can't eat, tomatoes anymore. Yeah, exactly. Yeah, acidic. Wine, acidic. Although I kind of been adding a little more base to it, so it'll be a little more basic, so I can still have it. But hold up. Soda is acidic. Yeah, it's about the same, but that's because it's dilute. So, because soda has phosphoric acid, right? So phosphoric acid is a strong acid, but it's such a small concentration that it makes it around the same as vinegar. Lemon juice is almost at 2, so that's citric acid. Still it's considered a weak acid. Gastric acids are strong acids. That's basically hydrochloric acid, right? So those are just, and then depending on the concentration of your hydrochloric acid, it just gets increased. So 1 molar hydrochloric acid is at 0, okay? And then if it's greater than 1 molar, then we know that it's going to be less than 0, right? It's going to be a negative value, okay? So base, we know that base, sea salt. Sea salt is a base, right? Egg whites, well, it's a base, it's greater than 7. Baking soda. Borax. Milk of magnesia. Do you guys know what milk of magnesia is? No. Milk of magnesia is what you use for upset stomach. It's kind of like bismuth. It has magnesium in it and bismuth in it. And so they call it milk of magnesia. You use it. It's clear, it's white, but Pepto has bismuth and milk of magnesia in it. And that gives you the pink color. And both of those make it basic. Ammonia. And then bleach. And then we have sodium hydroxide, different concentrations. Okay. You didn't know about that milk? It's not real milk, but yeah. Oh, really? It's good to know. Oh, yeah. Yes. Okay. So carboxylic acids are going to be the most common organic acids. So, and they have a pKa of about 4.76, well, it varies. So Acetic acid is about 4.76, pKa of 4.76. Formic acid is about 3.75. So is this a strong acid, weak acid, moderate acid? It is a weak acid, right? Because we already defined it. It's a carbon as a weak acid. Yeah. Okay, alcohols. Alcohols have a pKa of 15.5 and 15.9. Weak acid, strong acid, very, very weak acid, or beyond weak acids. Almost, yeah. So that's like weak, right? So we didn't even want to consider them acids. It's not even considered an acid, really. No. Okay, what about these amines? Methylamine, this is methylamine. Methylamine, this is ammonia. So we know that ammonia is a weak acid. Is it a base? Is it a ammonia is a base. So methylamine, we would assume would be a base, especially since the pKa is 40. It's greater than that of ammonia. So we know that's definitely a base. Okay, so not always, because we're gonna hold your horses. So it just depends under the circumstances. Okay. Now, see, this is the thing about carbon moieties, right? They have the ability of getting other things added to them, right? Because of that carbon, makes a little bit of horish, right? So in this case, we have protonated methylamine. Well, it's an amine, right? But look how it changes the pKa. Is it a base now, or is it a weak acid? It's a weak acid. Okay. So this is what you guys need to understand, and this is why the concept of what an acid is going to be really important. So if we're adding that that H plus, right? Then we're protonating it. We're making it a little more acidic than what it was initially, right? And you're going to have this happen in quite a bit of cases, right? Let's say in the case of amino acids, carboxylic acids, right? Or so in the case of an amino acid, you have an amine group on one side, and you have a carboxylic acid on the other side, right? So what happens under the right circumstances, you can protonate the amine and then take away from that carboxylic, right? Making that not minus, okay? And it can affect the behavior of that particular amino acid, whether it binds, whether it doesn't bind, whether it I should say not bind, but whether it ligates or comes together, okay, polymerizes, okay? The plus is actually on it's on the whole product, but it's really on the N as a whole, right? Because you're adding it's H plus that you're adding, right? So you're actually adding plus, but it's bonded together. It acts as a unit. So it's on that NH3 plus. So if we draw that structure, it's going to act like a base, yeah. Yeah, because we just saw it was like 40, right? pKa 40, which is like really basic. So that N is there now receptive for something to happen. Okay, but you got to remember, this is like that's a full functional unit, right? Okay, and that's the same thing that's over here. So here's an example of protonated alcohols. Okay, so that basically means that now we're adding that H plus to that O. Okay, now look at the pKa value. So is that a base or an acid? Strong
Acid.
base. It's an acid, strong acid, very strong acid, right? So we went from a carbon moiety being weak to now being a strong acid just by the addition of that H plus. Okay. Okay, and because we're having that protonation going on, we're also going to have that hybridization, right? So now that oxygen is going to be an sp2. Remember hybridization? We talked about it last week. Yeah, no, maybe. Well, you guys are worrying me here. I'm getting the bobbleheads, you know, I haven't got any. Okay. So alcohols like water can behave like a base or an acid. Okay. So here, this alcohol now is going to behave like a, since it's with a base, it's going to behave like an acid. Okay. Where if we have the hydronium ion, so this is the hydroxide ion, if we have the hydronium ion, it's going to behave like a base. Are you with me? You have that look. Good? You're good? Okay, so here, because we have this this base here, this guy is going to behave like an acid. It's going to give up that H plus. Okay, so now it's going to give up an H plus. That means that this guy can form water, and then we form this conjugate base, right? Where this guy, in this case, is going to behave like a base because we have the hydronium ion that's going to be donating its proton. So in that case, this guy now forms its conjugate acid. Okay, so kind of like water, these alcohols under those circumstances can act like a base or act like an acid. And that's because you have the oxygen and the hydrogen, right? That oxygen allows that for that to happen. It's able to get, either can get rid of that hydrogen or it can take on another one, okay? Okay, so yes. So it deals with that now, the concept, right? So it's still that H plus, right? So in this case, this guy is going to be giving up H plus, right? So in that case, so when we take a look at it, it's called an electron donor. So we kind of redefine how we classify acids, okay? We're classifying acids right now as, so it says the curved arrow points from the electron donor. So now we have electrons that are being donated, right, from the base. So our base is our electron donor, and our acid is going to be our electron acceptor. So this goes from the definition of there's two different mindsets. Proton donor, right? Proton donor means that you're donating a proton. You're donating the H plus, right? Compared to electron donor, right? So the Arrhenius model is based upon the proton donor. So Arrhenius acids are when you're donating a proton. The Lewis acids and bases are when you're donating electrons. So a Lewis base is an electron donor. So here, we're donating electrons. We're giving electrons to this guy, right? So now this guy gets those electrons, and this guy gets that proton. So the acid is the electron acceptor. The base is the electron donor. Make sense? So I know, and it's weird, like, and so we're trying to move a little bit away from that concept of the proton donor. Now to make it so you guys look at it as the electron donor. So a base is going to be electron donors, right? Okay. Base is going to, because it has those extra electrons. Base has extra electrons. It's going to be able to donate those electrons. Okay. And then the acid is going to be the proton acceptor. Okay. I mean, not the proton acceptor, the electron acceptor. Right? So if the base is donating, the acid is accepting it. Okay. Okay. So because we know that base are typically going to be that negative one, so it's going to be donating its extra electrons there. It's going to, hey, you take these electrons. Now, this is going to be important for OChem because that's what it's going to be based about. It's going to be based upon the movement of the electrons. Okay. And so if you guys get that, your mind wrapped around that, it's going to help you a lot. Okay. That was the hardest part for me. I'm like, because I was a Arrhenius boy all the way. You know, I understood that proton, you know, proton donor. I'm like, I got that shit down, you know, and like, and then you're throwing us with these electrons. I'm like, what's going on? But as soon as you get that wrapped, your mind wrapped around that, it's going to make it a lot easier to start seeing it. And you're going to see where nucleophiles are formed. Okay. And that's going to be important. The electrons, so bases donate electrons. Okay, so bases are going to be electron donors and acids are going to be electron acceptors. Okay. Yes. Yeah. Yes. Yeah. And so the way it's going to work is that now this guy here, it donated those electrons, right? It's like, oh, we're going to knock this guy out. We're going to donate that electron. And then these electrons are going to be used to break those bonds. So then it frees up that H plus, and that H plus is now able to interact with this guy. Okay. And that's the other thing that we need to start thinking about. Those electrons are going to be used to break bonds. Okay. And you're going to get the formation of new bonds. So we got a new bond formed here. And so in this case, we got a new bond formed here. Okay, so here's carboxylic acids. So again, carboxylic acids gives them some flexibility. They can act as a proton donor. Electron donors or electron acceptors. So in this case, the base is actually donating its electrons. So it allows this bond to be broken, and then we form a new bond, new water bond, right? Okay. And then in this case, where this base is donating its electrons, and then we're forming a new bond up here, right? And so because we have this OH here, right? And also because we have the double bond here, it allows it to have flexibility, right? So in this case, we're using that OH, right, to accept those electrons. So if we have an H available, we can accept those electrons, right? So basically what you're doing is you're taking that H plus and you're donating those electrons to this guy. Does that make sense? Where here, we're taking these electrons here and we're donating these electrons here so that this guy can now get that H plus, right? So they can form it. Do you guys see that? So now it's important that you guys pay attention to this too, because two different modes of attacking, right? You're not using the same case, right? So water was real simple because you only had HOH. So you're just going to use one of those, you know, either you're going to take it on or you're going to remove it. Where here, it's going to be dependent on where it goes. Did I move too far? Got ahead of myself. Okay, so does that make sense? This allows for that flexibility. Okay. Okay, so same thing here with the nitrogen. Nitrogen does exactly the same thing. So in this case, nitrogen is able to sit there and take the electrons, right? And then we can get this H plus, right? So amines, basically, right? And then in this case, it can use that lone pair of electrons as a donor. It's donating it. Okay. Are you with me? Yeah. Yeah, it has flexibility, right? So it has flexibility. The question is, you're basically asking, can the same thing happen in the same solution? Well, if you have a mixture of both, yeah, technically it can. So if you have one that already has an acid and a base that's there, but you also could probably going to get the acid and base interacting with each other as well too. So usually you only have one event happen, right? So if you have that base, this is going to be what happens. If you have that acid, this is what's going to be happening. Okay. Are you kind of got it? Okay. So protonated alcohols are going to have a pKa that is less than 0. Protonated carboxylic acids are going to have the pKa that is going to be less than 0. And protonated water, we already know it has a pKa of less than 0. Right? So if it's the normal carboxylic acid, its pKa is about equal to 5. If it's protonated amines, it has a pKa of about 10, which is still a weak acid, right? So this guy's a weak acid. And then alcohols are really, really weak acids, to almost base. So, okay. How are you guys doing? And you're hanging in there. And the pKa of water is 14, right? What's that? We will do examples. I'll go through and go through some examples. Okay. Okay. So yeah, I need to start adding a lot more examples to the slides because they don't give you too many. Okay, so let's see. Since you asked for it. What? Let's see. Yes. Yeah. Understand it. Let me get to a whiteboard. What are you saying? Are you saying that my stuff is hard? Is that what you're telling me?
I don't know how I'm gonna answer it. Kind of forget everything. Because my mind is like blank.
Okay, so let's see.
Since we have enough time for a project.
Yeah. Yeah.
There's a lot to cover.
There's a lot to cover. You're not getting the whole organic chemistry one.
That's a lot. I mean, I got the past couple of times.
Well, yeah.
I know, I really need to do it.
What was that?
It's because the previous classes never had any projects, any projects in them. So they were like a lot already. I like them, yeah, but I feel like there's a lot of
Exactly. But that's what I want you to think about the concept, right? And apply it. I think typically the reason I give projects is because when you guys get in the real world, you need to be able to apply stuff. And that's the problem. You get in there and you guys are book smart. You understand what's going on book wise. But when you get in there and you're like, okay, so now I'm in a lab and I'm working and I have no fucking idea what I'm doing, right? And so that's what I hate. And I get students, like the students that would come in when I was working in the industry. I'm like, Jesus, you know, they'd be 4.0 students and all this and all that. And then they can do the simplest thing, like make a solution, right? Because they have no sense of application, right? They did in a lab, they did, the instructor told me to do this and this and this and this and this. Well, I'm not going to be here to babysit you the whole time. I need you to be able to read and apply what you know to do these things. And so that's the projects helps you get to that point. No. Look at her. She's always okay. Sampula is always negotiating extra credit. Okay, so. Yeah, I just haven't given it to you yet. I will be giving it to you. Okay, so let's see. Okay, so we'll start simple. We'll work our way up to things. And so let's see. We'll do.
I can't see the screen anymore.
Can't see the screen anymore? Okay, hold
No.
on. Is it a whiteboard? You don't see a whiteboard at all?
No.
Okay, so let me see what's wrong. How about now?
Okay, I can see it now.
Okay, so I want you guys to draw the conjugate acid of these compounds. See? So this is ethanol. Yeah, this is the easy one. It's a piece of cake. The conjugate acid. The conjugate acid of this guy. This is A. This is B. This is C. This is D. Now you're going to assume that you're interacting with, not with water, a base, right? So you're going to assume that you're interacting with the hydroxide. That's what you're going to assume that you're interacting with. So I want you to draw the conjugate acid for that. C, we'll go C. Okay. Okay, so we can do A together. Okay. So we're saying C, H, 3, C, H, 2, O, H, O plus. Oh, wait a minute, hold on. My bad. Conjugate acid, so that would be, let me clear this. It's not, sorry, it should be hydronium ion. That's with a true acid-base reaction, but you need to stop thinking of it like that now. Now you need to think of it as a conjugate acid and a conjugate base, right? So you're going to produce a conjugate acid and a conjugate base. So if this is my base, and this is my acid, I gave you the wrong thing. It should be H3O plus. Okay. Yeah, not hydroxide. That's when we're producing our. That's when these guys are going to be acting as a base. I mean, an acid, and then the hydroxide acts as a base. So now these guys are acting as a base, and the hydroxide is acting as an acid. So if I have this happening, what's going to happen? This is the reaction. What are going to be my products? The other O, that's right, because the O is going to be able to accept, right? So now we have C, H3, C, H2, and then it's O. We're going to have one attached here, one attached here, and this guy's going to have a plus associated with it. And then we have those two. Yeah, it would be near the oxygen. Let me move it over. Maybe. I hate the screen. Okay. Okay, so then it has that whole unit, the HOH, has a plus charge associated with it as a whole. Okay. Actually, the molecule as a whole, it has a plus charge associated. And you guys, so you're getting used to it. You got to remember electrons are mobile, right? So then that means that the charges are going to be mobile. So it just represents. So even if it was on that H, it really represents the whole molecule because it's a movable thing. Yeah. They'll mark it around. Yeah. 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 Which is dumb because it really, you guys, the electrons are mobile. They're not stationary. And that makes it seem as if it's stationary. So, but yes, it should be put next to the oxygen because that's where you're going to have that adjustment happening. The next thing that's going to be able to attach is going to be attacking at that oxygen, right? Or the carbon, between the carbon and the oxygen, depending on what it is. Okay, so this would be our acid. Then what is going to be the conjugate acid? What is going to be the conjugate base? Water. Yep. So it's in the room plus H2O. Okay. So in this case, these are all bases. Now we're going to make them into conjugate acid. I want to know the conjugate acids.
The arrows just arrow.
Yeah, it should matter. Yes. So although I did it wrong, let me fix that. So we know that it's in equilibrium. Which side do you believe is going to be favored? This side or this side? You say the product is going to be favored? Yes, the reactant. In this case, the reactant is going to be favored because this is guys, you're going to have more abundance of this guy than this guy. Right? Ooh. Well, actually, no, let's think about it. So we have the ethanol. What is the pKa of ethanol? It was like 15, right? So then if it's 15, then which way should be favored? It actually should be the other way, right? No. Actually, that's right. If it's 15, ethanol, it's 15, and then now this guy's P. So this conjugate acid is going to be a greater pKa. So then it actually should be favored the other way. So you're right. You were right initially, Israel. So it should be this way. My bad. Yeah. There you go.
So the larger pKa, the more it's favored.
That's right. It's going to favor the side because the smaller the pKa, the more it's favored. So in this case, the pKa of this guy is going to be favored compared to over here, right? And we know that because we know that protonated alcohols are going to have a negative pKa. So then that means that we're really going to be driving in the other direction, right? Protonated alcohols, protonated carboxylic acids, protonated water are all going to be driving. Okay, so the second one, which is H3, C, O minus. Thank you. Okay. So that's going to be reacting with H3O plus. So what are we going to get? And I shouldn't draw it like that. I should draw it. We'll just do it like this. What is going to be the product and which way the arrow is going to go? CH3, CH2, OH. Plus water. Okay.
I don't know if I'm right, but I put the arrow as favoring the reacted side.
Saying go in this direction.
Yeah.
Okay. Do you guys agree or disagree? Because the H plus, but the H plus was added in the other case. Was it not? It was added to, like in the case of just the ethanol, it was added to this guy. So we have a dispute. Okay, so let's look at the on this side. This guy has a pK of what? What's that? Okay, so it's a pK of 15. All right. And then this side has a pK of what? This is a little tricky here because we know that this guy is going to be, is that going to be a lower pKa or a higher pKa than this guy?
It's going to be higher.
This should be a higher pKa, right? So this guy should be a much higher pKa over here.
Oh, so that means it
Oh.
would favor the products.
That's right. So Pula is correct.
Like a lot of like hydrogen ion is being added to pKa. That's how I'm.
Yeah, because you're basing it upon your acid, right? And so it just, I have to think about what you just said. You got to say that one more time.
Well, the H plus is being added.
Uh-huh.
It becomes a little bit more acidic.
Okay. Yeah, that's
So
true. Uh-huh. Yeah, but it's going to be dependent on where you're starting at, right? So the reason why it worked out is because the pKa on this side is much larger than the pKa. Much larger than the pKa on this side, which means that we're driving this reaction. We're driving it to the other side. Where in the other case, it was the opposite. That pKa, this pKa over here is much, much smaller, right? So, right. Yeah, so larger is going to be driving to the smaller side, where in the other case, it was the opposite direction. Does that make sense? I think. Let me see. Let me think of another way of explaining it. I have to think. But you're correct. I'm trying to see if how your logic is thinking. You know how. Yeah, it's holding up. Yeah.
I just thought of, the, H plus added,
Yeah,
it becomes more acidic.
that's right.
And so since H plus, like I thought, okay, there's no, H plus on that. It's an H plus is being added to CH3, CH2O.
Hmm.
So obviously I thought, okay, if an H plus is being added, it's going to be a bit smaller than
The other side.
the
Okay.
other side. 'Cause
Okay.
I don't know. I don't know.
I'll have to think on that. Yeah, I have to think on it. Yeah. You say good luck. We'll go back to the last one. Yeah. 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 So the stronger the acid, the lower the pKa, right? Mhm. So we know that this guy, the pKa for this guy is really, really high, right? Okay. This guy is going to be low, right? It's going to be a low pKa. But then over here, these guys are going to be, they're going to be high, but not as high as this guy is. You understand? Yes, it depends on the players, right? So, yeah. So it depends on the other players, okay? So does that make sense? The pattern. Yeah. Okay, what about the next one? Well, we know conjugate acid, that's the main part. Is that it? And then we'll work on the arrows here. Okay, what about the next one? It was this guy. Did I give you the next one? I think I didn't give you the next one. Did I give you this one? I didn't give you this one, I don't think. Okay. So I gave you, yeah, I didn't give you that one. Okay, I gave you this one. So CH3, CH2, NH2, okay, what's going to happen here? Okay, so we're good. Whoops. Okay. Okay. Okay, so this guys are going to give me what type of acid is going to be a strong acid, going to be weak acid. Is it going to be less than 0 or greater than 0? Is it going to be around 10? Okay, so is that going to be a strong acid, weak acid, or which one am I going to favor? Okay, so NH3 ammonia is, this guy is 36. Okay, and then this guy is, are you saying this guy here? The NH2, right? Isn't that one the 36 one? Okay, so but this guy is 36. Okay, so if this guy is 36, then which way are we're driving? Which way is it going to be? Are you sure? Yeah, so the pK for N3 plus. Okay. Okay, and what is the pKa for N? Yeah. So this guy's around 40, right? And then this guy's around 10, right? So we're going from 40 to 10, okay? So who are we driving? Huh? Mm-hmm. But is it, okay, overall, now let's look at the overall thing, right? So now with this, we're getting a pKa of this guy overall is going to be what? pKa of 10, roughly? Overall 10, okay? So is that going to be favoring which side? pK of 10, approximately. Is that weak acid, strong acid, or if the overall pKa is going to be about a 10, because that's what we're getting from this product, right? Is it going to be 10? Which one are we going to favor? That's a little bit stronger. Okay. Yeah. So this guy, who you said was a pKa of 40, right? And now with the addition of this guy, we've gotten it to be a pKa of 10, right? So, but overall, we're having, if we take this overall, the whole thing all together, we're going to get there. So we haven't got there yet. I'm ahead of the game. So we got one more thing to teach you, and then you'll be able to distinguish between, yeah, which one is the best, the overall equilibrium of it. Okay. So, but right now you guys think it's this. Hold on. You're favoring the products, right? Again, you think it's this. Is that right? Based upon your notes. Okay. Yeah. Yeah, but remember, if it's less than 1, right, then that means it's a strong acid, right? So we have a weak acid, and I see what you're getting at. Okay, so this conjugate acid, is that going to be a weak acid or is that going to be a strong acid? Because it has a pK of 10.
It's a weak acid.
It's a weak acid. And then, but we know that this guy is even weaker, right? So that's what you're basing everything on. Okay. Okay, we'll get to this here in a second. Okay. It's the same. No, we did talk about that in this case, right? Because it's the same concept, right? So this guy is a weak. That'll be weaker than this guy. This will be a really, really, really high. I should say, this is a really, 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 really weak acid, right? This is a weak acid, right? Because this guy is like pKa of what, 10? Alcohols. Are they 10 or greater than 15? Okay, so 15, and we know that this guy has to be much greater than that. So very similar process, right? But we'll get into how to do the calculations more exactly. Okay, there's calculations, there's numbers. Right now we're predicting, right? We're estimating. Yes, we're quantitatively guesstimating. Okay. Yeah, but you guys are doing pretty good so far. Chalk it up. Yeah. Agree. Okay, so let's see, we're going on time. 2:30. We're going to take a break here in a minute, but let's do the last one. So the last one was so it's OH. Oops. Nuts. Okay. What's going to happen there? This is going to be my acceptor.
The oxygen.
Which one? There's 2 of them.
I put it the one that was double bonded to carbon.
That's right. Okay. So, because of what? Because of the yield symbols. Just don't use equal signs. Because these guys have easily available lone pairs, where this guy, if you look at it, it's OH, right? So you already have this H here that's kind of shielding it, but you still have these lone pairs that it could technically use, right? But it's easier for it to use these lone pairs rather than the other one. So, because these guys have 2 lone pairs that are readily available, where this guy has more of a shield. And exactly, yeah. And that's the other thing about organic chemistry. It's about accessibility, right? And so sometimes you have to add things to help with the accessibility. Okay. Questions? Mm-hmm.
So for that last one, it favors the product side.
On the last one, it favors the product side, yes.
Okay.
And here, you're asking me, do I put a positive? That's right. And it's balanced out by that plus, yeah. So it neutralizes that. So, yeah. Okay. Questions? Concerns? Wait. Okay. Okay, let's take a, we'll say a 5-minute break. Is that okay? My butt's sore and I'm hungry. Okay, are you guys ready? Yeah. No, you're not going to be able to turn up anything. No, what I'm going to teach you now is we're going to talk about how you're going to be able to determine the pKa using your reactants and your products. Okay. So. Me too, gosh. Okay, so here we have a combination of, let's see, of two compounds that are interacting, right, in your reactants. So we have our hydrochloric acid, HCl, and we have water. This is the pKa of HCl. This is the pKa of water. Which one is going to be the acid in this case? Hydrochloric acid. Okay. So what was that? Yeah, it has a negative value for the pKa. We know that it has a very, is it a strong acid, or is it a weak acid, or is it a mediocre acid? What was that? It is a very, very strong acid, right? So we know that hydrochloric acid is a very strong acid because it has a negative value, negative 7 value. It's much less than 1. Okay.
Hey, Dr. Henry.
Yes.
It's just showing the whiteboard on
Oh, sorry.
screen.
Thank you. You got to remind me. Otherwise, I'll just leave you in the. How about now? Can you see it now?
Yeah.
Okay. Yeah. Thank you. So hydrochloric acid is a strong acid, where water is a. In this case, in this reaction, is it going to be the acid or is it going to be the base?
The base.
Base. Okay. So in this case, it's going to be the base. Okay. So in the case of the ammonia and the water, who's going to be the acid?
The water.
The water, right? So we can determine this by their pKa's, right? We know that the one that has the lowest pKa is going to represent the base in that circumstance, right? The lowest pKa is, sorry, it's the acid, sorry, not the base, is the acid, represents the acid, okay? The one that has the lowest pKa represents the acid, okay? So if the one, when you have two of the things interacting, the one that has the lower pKa is going to be our acid. It's going to act as our acid. Okay, so that means that it's going to be accepting the electrons. Okay. Okay. Does that make sense? Okay. Okay. So if it has a higher pKa, then it is a base. Yes. Then that means the other guy's going to be the acid. Okay. So let's see. Let's do this. One second. Okay, so if I have I wish Zoom had subscripts. It would make my life easier. Okay, we have methanol. And methylamine. Okay, which one is going to be the acid? Which one is going to be the base?
Do methanol
Okay,
is going to be the acid.
so this is going to be the acid. And why is that?
Well, if I remember correctly, it should have a lower pKa than the other one.
That's right. This guy has a pKa, what was it, 40-ish? Yeah, so 40-ish. And this guy has a pKa of like 10, right? Okay, so makes sense. This is a methylamine. That's an amine. Yes. It has a higher pKa. It has a pKa of 40-ish, right? And this guy has a pKa of 10. So which one is going to be, yeah. Okay. So let's go, we're going to go back just a little bit to make sure that you guys understand. And this is going to be something you guys need to recognize here now, and you're going to get, it's going to be reinforced. Okay. So let's go back to our structures here. Okay. This here, that is carboxylic. That means it's a carboxylic acid. The double bond, the C, the OH. Okay, so that represents a carboxylic acid. It's also written as COOH. So, and we'll put an R here. R means any functional, any hydrocarbon, okay, or any functional group, any group. So it could be anything, right? So this is like the root of a carboxylic acid. Okay, carboxylic acids, we know that they're going to have pKa's that are going to be lower than alcohols, but not, they're going to be weak acids, naturally weak acids, right? So carboxylic acids will fall in the weak acid range. So, and then you're going to get your pKa's around 3-ish to 5-ish in that area, somewhere in there. So, alcohols, let me clear. Those guys are always going to have OHs. So it's going to be a hydrocarbon attached to an OH. So hydrocarbon attached to an OH. A hydrocarbon attached to an OH. That makes an alcohol. Okay. So, and these guys are going to be in 10 to 15 ranges. 10, I guess, 10 to 20. What was that? Okay. I'll try to pronounce it a little bit better than carboxylic. Carbox, like box, boxylic. That's right. Okay, so these guys are amines. Now, amines could have, well, all of them could technically have primary, secondary structures, but amines basically have nitrogen. Okay, so this is a primary amine. Okay. So what makes it amine is that nitrogen. Okay. And then we talked about protonated, right? That just means that we're adding, protonated basically means we're adding that H+. We're adding a proton. Okay. Okay. So now, okay, let's see, clear. The equilibrium favors the formation of the weaker acid. Okay, so the equilibrium favors the formation of the weaker acid. This guy is the stronger acid. This guy is the weaker acid. So we're going to be driving the reaction the other way. Okay. Here, this guy is the weaker acid. This guy is the stronger acid. So then we're going to be driving it in this direction. Okay. So here, we're going to take a look at, so in this first case, the pKa of our carboxylic acid is going to be, so it's the P equilibrium, sorry, pKeq is going to equal pKa reactant minus pKa product. Okay. So if our pKa reactant minus pKa product, so our pKa of our reactant is, in this case, for this carboxylic acid, so it's proteonic acid, so it is 4.8 minus the pKa of this acid, which is 9.4. This guy gives us a negative value. What is that? So that's 4.6. Negative 4.6. Okay. So it's a negative 4.6. So that means that this value, it's going to be favoring which one? Is it going to be favoring the stronger acid? If it's in this case, it's going to be favoring the weaker acid. Remember, it's always going to favor the weaker acids. So it's going to go towards the product. If the value is a positive value, let's see, actually they both should be. So in this case, 15.6, I mean 15.9, sorry, minus 10.7. That's going to give me a positive value. And that's going to be what, 5.2? Is that true? So then that one is going to be favoring the reactants. So the arrow is going to be bigger in the reactants. Negative products, positive reactants. Okay. You got it? Simple, not too hard. Okay. Okay, and this is how we calculate our equilibrium constant. pKa equals pKa reactant acid minus pKa pKa product acid. Okay, and you guys understand what pKa means. So then that means that the equilibrium constant for this reaction is going to be 4.0 times 10 to the 4th, because we know that P means minus log. So anytime you use your P, that's going to be equal to minus log of whatever you're talking about. So in this case is our KEQ. I hate the screen, it drives me crazy. Keeps going in and out. Okay, so since we know that this is what that equals, then we know that KEQ is going to be 10 to the 4.6 in this case. Make sense? Okay, good. Okay, how are you guys doing? Your brains are still working, functioning? No? No? Still rotating? So it's always going to favor the one that's the weakest, right? So then you're going to go towards the one that's the weakest. So if we go back, look at the pKa of both sides. Let's see. Clear. Okay. This guy's my stronger. This is my weaker, right? So it favors the side of the weaker acid. That has the largest value. Yep. So that would be weaker. No, you guys actually had it right because you're looking at, so on one side, your acid is H3O, it's H3O plus. That's the stronger acid. So you guys had them all driving towards the product, right? Which is always going to be that weaker acid, right? Because the H3O is much stronger than all the other ones. Yeah. That's right. Yeah. So you guys got them right, but yeah. Yeah.
That was done on the nose, but it was the yielding part.
But that's because it was with the base. If you take a look at the notes, one is done with the base and one's done with the acid. So in both cases, you want to look at the acids. So you want to look at acids on both sides. So in this case, this is the acid on this side, and this is the acid on this side. And that's what you're going to use to determine. Do you understand what I'm saying? Yeah. Yeah. So yeah, if your value, the easiest way to remember it, it's always going to go to the one that's the weakest, because you're going to be driving in that direction, the one that's the weakest. Okay, so if this guy is a strong acid, it's going to be pushing it in this direction, right? So then it's going to favor the production of that weak acid. And then in this case, do you have the example? Well, it's okay. So the strong acid is going to be more likely to dissociate. So that means that it's going to break apart more than the weak acid, right? So if this guy is a strong acid is over here, then we're going to be pushing the reaction this way because it's going to dissociate to those things. Oops. I don't know how I flip things. I don't even touch it. Maybe my elbow, I don't know. And then on the other way, right here, this guy is the weaker acid. This guy's a stronger acid. So this guy's going to be pushing it that way because it's going to be stronger dissociating, right, than this guy. Okay. 16. Okay. Mm-hmm. Mm-hmm. This one here.
Yeah.
Okay. So in this case, right, let's see. So which one is going to be, so this guy is acting as a base, right? This guy is acting as an acid. Oh, I see what you're asking me. And then you're saying that this guy is the stronger acid than this guy, right? So this guy is, I think it's like negative, it's, no, it's right at 1, right? So this guy is at 1 here. The pKa is about 1 for the hydronium ion. And then this guy is, the pKa for that one is like a negative something, right? So which one is the stronger acid? Yes, it has to do with, well, it has to do with that. And then also because this is an extra OH on top of it, it gives it that even lesser charge. So yes, so in this case, this guy is going to have a lower pKa than this guy. The pKa of protonated, if you guys take a look on that table, I think we have mentioned it. Protonated carboxylic acids less than, okay, yeah, less than 0. And if you look at the value is actually a negative value compared to this guy. So this guy is a weaker acid than this guy. This value, this guy has a negative value, right? This is going to have a higher negative value than this guy. This guy is going to be about 1-ish, right? So is the strongest, right? Remember, yeah, so then we're favoring the other guy because it's a weaker acid. Yes, so we're going to be favoring it. We're going to be pushing it to the one that is the larger pKa, yes. So the arrow points to the one that has the higher pKa. That's what you're saying, which is the weaker acid. Yeah. Does that make sense? Yes, you're supporting the weak, yes. That's right. Yes, the PEQ, yeah, okay. P equilibrium, not pK equation. Yeah. Equilibrium, we don't want to get, okay. Are you guys with me so far? Okay. Okay. Differently. You got and the funny thing is that you guys got the answers right, but you're thinking about it. Well, yeah, but in a different way of thinking about it. Yeah. Okay. Let's see. Get that. Okay. Okay, so it does make sense now. Okay. Yes, and that's what we're getting ready to do. We're going to apply those, right? Okay, so this basically, we're going to use strength of the acid to determine the stability of its conjugate base. Okay. Okay, let's see. Funny, that's a. Okay. Slides. Okay, so here, the more stable the conjugate base, the stronger the acid. Okay, so if we look at these acids here, HF is a stronger acid than water. It's a weak acid, but it's a stronger acid than water, and water is a stronger acid than ammonia, and ammonia is a stronger acid than methane. Okay. So the stronger the acid, the more stable the base, right? So then this guy is going to have a more stable base than this guy. Okay. So the fluorine ion is going to be more stable than the hydroxide ion, which is going to be more stable than the, oh, I don't even know what to call that one. The amine ion, and then the methyl ion. Okay. Methyl cation. Okay, so we know that this guy is going to have less stability than the fluoride ion. Okay, now we know that the electronegativity is going to affect the acidity, right? So this guy is more electronegative than O. This guy is more electronegative than N. This guy is more electronegative than C. So because of that, this guy is going to be a stronger acid, right? This guy is going to be a weaker acid. This guy's going to be even weaker. This guy's going to be even weaker. It's going to be our weakest. Okay. Yes, they're all weak acids. Fluorine is, like, if we compare fluorine to chlorine, chlorine is a much stronger acid than fluorine, you know? So, say hydrofluoric acid is a weaker acid than hydrochloric acid, right? Significantly weaker, right? Okay. Questions? Concerns? So, and then also size. Size is also going to play a part in it as well. So when the atom size, okay, so when they're the same size, then it all is going to be dependent on the electronegativity. But as we go down, we know that that affects the acidity, right? So, because we know that the acidity is associated with getting rid of that hydrogen, right? So we know that the hydrofluoric acid is going to be like, nope, 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 you keep your butt right here next to me, right? Where the hydrochloric acid is going to be like, girl, do whatever you want to do. You're your own woman. And then the hydrobromic acid is like, I'm going over here. I don't care where you go. And then the hydroiodonic acid is just like, I don't care. You do whatever you want. Go across town. I don't care, right? So you see the difference, you know, so as we get further away, the easier it is to get that hydrogen off. And so that size also plays a part in it as well, too. The fact that we're tiny, right? And we're, let's say, the hydrogen, the oxygen, and the nitrogen, and the carbon, they're all about the same size. They're a little bit different, right? Fluorine is smaller than the others, right? But a little bit only. So they're roughly around the same size. But then it deals with the electronegativity at that point, right? It's going to be solely on the electronegativity because, you know. Okay, so why are alcohols stronger acids than amines? Now, if we just said, based upon this, right? So strongest, weakest, right? So alcohols, why are alcohols stronger than amines? Because it has an OH, okay? So then that OH, that O particularly, is able to do what? It's able to hold on to the H, okay? Where the N is less. So when we say it, oxygen is more electronegative than nitrogen, right? So it's able to have a stronger connection with them. Okay? And so we look at our pKa's, 15.5, stronger, or is it weaker? Stronger. Okay. Okay, so why are protonated acids stronger than acids than the protonated amines? Why are protonated alcohols stronger than protonated amines? Same reason, right? It's not going to be any different, right? Exactly the same reason. Okay. So hybridization also is going to affect our electronegativity. And if that affects our electronegativity, we know that affects how strong that acid is. Okay. So if it's sp, it's going to be more electronegative than if it's sp2, than if it's sp3. Oh, let's take a look at that. Wait a minute. Hold on. sp. Okay, let's do this. What is this guy? I'm getting there. I'm trying to circle. I'm just circling it on my screen. It's just not doing it right now. So, okay, this guy. Can you guys see the little red dot? Okay, so that guy. What would be the electron? I mean, the hybridization for?
Wouldn't it just be SP?
So this guy would just be sp. This guy would be
SP2?
okay, or is it? Is it sp2 or is it sp4? What's that? sp3. And then you have the lone pair and the, okay. And what about the nitrogen here? All sp3s, right? Okay. So, let's go back. sp2s are going to be more electronegative than, sp is going to be more electronegative than sp2s, and sp2s are going to be more electronegative than sp3s. So if we have a triple bond, right, triple bonds are going to be a stronger acid than the double bond. The double bond is going to be a stronger acid than, okay, than the single bond. Okay, so if we looked at in terms of acidity, this guy is going to be the weakest. This guy is going to be in the middle. And that one's going to be the least. Okay, make sense? Okay. Okay, and again, so which one is the least stable? Which one has the, let's say we'll look at it like this. Which one has the shortest bond length? Triple bond, single bond, double bond, or single bond?
The shortest bond length?
Yeah, which one has the shortest bond length?
The triple bond.
The triple bond. Okay, so we would say this triple bond, would you say is more stable than the single bond? Because you have those extra, you had that extra connection. It's also shorter, it's tighter, right? So which one is going to be the strongest acid? Triple bond, right? Okay, so this gives us our pKa values. So we have methane is 60, ammonia is 36, water is 15.7, hydrogen disulfide, dihydrogen sulfide is 7.0, hydrofluoric acid 3.2, hydrochloric acid, hydrobromic acid, hydrodonic acid, right? Exactly what we thought, right? Yes, no, maybe. Yeah. So in this case, as we go down the periodic table, it becomes stronger or weaker acids? Stronger, okay. And that's the same thing here as we go down the periodic table. These guys are right underneath each other. Stronger or weaker acids? Stronger. Okay. What's that? There's a lot to consider. Yeah. Yeah, so that's also one of the things that make OChem interesting. Let's see if I can get a question for you here. Okay, let's see. Okay, so which one of these are the stronger acids? Let me go back. So I'm gonna write it on here. So we have okay. A or B? Which one would be the stronger? Sure. How many people say A? Raise your hand. How many people say B? Raise your hand. And you got to vote.
B.
Which one is the strongest acid? A or B? 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 Okay. Correct answer is B, right? Because as we go down the periodic table, it gets bigger. The bigger it gets, the more acidic it gets, right? Okay. What about, let's see. Now what about this one? C H3, C H2, C H2, and H3, or C H3, C H2. I should grab my plus here. Sorry. C H2 O H3 plus. Oh, sorry. Screwed up. It should be 2 plus. There we go. Which one is the stronger acid? So A or B? A or B?
B. B.
Do you guys all agree or anybody disagree? The correct answer is B. Why?
Because oxygen is more electronegative than nitrogen.
That's right, because oxygen is more electronegative than nitrogen. Okay, you guys got it? Yeah, that look. That's right. It was because of the size. Okay, when they're the same, when they're on the same level, then you have to look at the electronegativity. When they're on different levels, right? They're underneath each other on the different levels based upon size. Okay, so you have to take both in consideration. So, okay. Okay. Okay, so clear. Okay, so stronger acids are going to have a more stable base, right? Conjugate base. Okay, so stronger acids are going to have a more stable conjugate base, which means it's weakest, right? So if you have a strong acid, you're going to have a weak base, weak conjugate base. Okay. Okay, let's see. Okay, so substitutions can affect the strength of the acid. So here, right here, we have hydrogen, right? So this guy is a weak acid. But as soon as we start adding the halides to it, well, this guy increases that strength, right? And then this guy, makes this a stronger acid. This guy makes it an even stronger acid. And this guy makes it an even stronger acid. Okay. And the reason why is because now you're playing with this guy over here, right? So you're pulling the electrons over to the guy who has a stronger electronegativity. So this guy is the acidic part of it. So now we're playing with those electrons and we're pulling it to this guy, right? So if we're pulling that electron, that means that this guy is going to be more acidic, right? Because this guy is more electronegative, it's going to have a stronger pull. You guys get that? Where this guy has a weaker pull. Okay, so because this guy is on the other end, it's going to be pulling the electrons from this side, the acid part of it. So it's going to be pulling that negative charge towards it. So the ones that have the most electronegativity, right, is going to cause that acid to be stronger, right? Okay, even though that this guy is smaller than this guy, now we're just looking at electronegativity because they're playing an effect on the other side of that acid. Does that make sense? So this, remember when I told you that look at him, his hair is all screwed up and everything. You're getting it? Okay. So in that case, right? So the electron is moving, right? We've got to think of the electron moving. So we're moving the electron from here to here because the stronger electronegativity. Okay. So you're getting induction. It's being induced. So you guys remember when we talked about induced dipole, all that stuff? Oh my gosh, it's coming back. Yep. Exactly, intermolecular forces. Now, it's going to also be dependent on distance. The further you are away, right, the less impact you're going to have. The closer you are to the part that's going to be the acidic moiety, right? Okay, so this guy is close. The bromine is close here, right? It's on that second carbon. Where here it's on the third carbon, and see how much it drops. Then here it's on the fourth carbon. Well, it gets even bigger. Here it's on the last carbon. And so this guy is going to be our weakest acid. This guy is going to be a stronger acid. The closer you are, right? And that makes sense, right? Because it's pulling. The closer you are, you have a stronger pull, right? So you're pulling it more. So that means that this guy is able to get that plus even better, right? So, okay, let's see. Okay, so my first question. Why is carboxylic acid a stronger acid than the alcohol? So, okay, so here's our alcohol. Here's our carboxylic acid.
Is it because the carboxylic acid has two oxygens?
It's because, that's right. It is because that carbon has two oxygens. So this oxygen is now pulling that electron away, right? So where here, this guy only has that one. So it doesn't have anything pulling it. So. Okay. So this is just basically showing you our delocalized electrons, moving electrons, right? So now we're getting this guy to move. And so we have these electrons that are being shared between these. These are the resonance structures. Remember resonance structures? Okay, so you're having electrons that are being shared between those two. So you're getting movement. So this guy is pulling that electron. So giving this a, both of these are sharing that negative charge essentially. Where in the case of, it only has that one. Okay. So this is just basically summarizing it, right? So you increase the electronegativity, you increase the acidity. You increase the size, you increase the acidity. Okay. How are we doing on time? 3:35. Okay, so we're gonna finish, I think. Okay, so we know that as we increase the number of bonds between the two, we also increase the acidity, right? So that hybridization plays a factor. When we do the inductive electron withdrawal, so basically the stronger the electronegativity is, the stronger that acid is on that other side when we're inducing. Here, location. It's location, location, location. Oh, this one is, yeah, this is location. Stronger than this guy, right? Okay. And then they forgot to put the one. Should add one here. We should add one there. This is a screw up, my bad. Okay. Oh, actually, no, it isn't. Okay, so in this case, because we don't have a pull, we're not having anybody pulling it on this one, right? It's going to be weaker than this guy. Yeah, yeah, even though it's wrong technically. So, yeah. Oops, sorry. Yeah. Got a couple of slides to fix there. Okay, so when we have delocalized, right? So this guy here, stronger acid, right? The base is going to be less stable. Strong acid, stable, right? So I say stronger acid, weaker acid. This guy, sorry, more stable, weaker base, stronger base. Okay. Does that make sense? Strong acid, weak base, right? So this is the conjugate base of it. It's a strong acid, it's going to be a weak base. If it's a weak acid, you're going to have a stronger base. Oh, you're doing this, yeah, it's up and down, yeah. Okay. So this is the Henderson Haasenbach equation. This is a quick way of determining the pKa. You guys remember this? You guys actually use this equation. All you guys use this equation, believe it or not. Because I remember I definitely had you guys do this part. Nothing else, but you guys did this. Okay, so the pKa is going to be equal to the pH plus the log of the concentration of the acid over the concentration of the conjugate base. Okay. This is 1B. Yeah, so this is the review of 1B. I knew you guys was going to come back, right? Okay. So let's see. So then this allows us to we're able to sit there and calculate our pKa, or from our pKa, we can calculate our pH, and based upon what we're given here, right? So, okay. So this part is the acid form. So then that's the part that's going to go up here. This is our base form. So that's the part that goes down there. Okay. Questions? Okay. Okay, so if our pH is equal to our pKa minus 2, right? So then that just tells us that our acid form is more favored, right? In this case, again, acid form is more favored when the pKa minus 1. So let's go back. So if it's a log, then we know that the pKa, which value is higher? If it's a negative value, if this log is a negative value, which one is going to be higher? The bottom or the top? If this guy is a negative value, if the log of the concentration of the acid over the concentration of the base is a negative value, which is going to be higher, your acid form or your base form? That's right, our base form. So if it's a negative value, that means that this value is, let's say for instance, 1/10. Log of 1/10 is what? Somebody do that math. -1, right? Okay, so if it's a negative value, we know that the base form is more abundant than the acid form. So what does that mean? If we're having more of the base form, which side is going to be favored than the acid form? Which way is the direction? Which direction is the arrow going? Towards the product or towards the reactant? Here's the reactant. This is the product. It's going towards, you said the reactant. It's going towards the product, right? Because we're favoring this guy, right? Does that make sense? You have less of this guy. So that means that you're driving the other guy is going to be more abundant. Does that make sense? You have more of this present because you're pushing the reaction more in this direction, right? So that means that this value is going to be greater than this value. If I have a positive number, then what does that mean?
It will favor the reactant.
It's going to favor the reactant. It's going to be just the opposite. It means that we're now going in this direction. It's going to be favored than this guy, right? Because you have more of this guy around. Does that make sense? So the arrow tells me which one I'm going to have more of, right? Which side I'm going to have more of. That's what the arrows tell me. The arrow is big in one way. That means I'm going to be producing a lot more of that side. No, you can't have both sides because here it's based upon the ratio between your product, your reactant over your product, right? So this is your product, this is your reactant, right? So both sides can't be. Do you understand? Okay, so here this says that this side, the bottom side, means that the base is 10 times greater in concentration than the acid. So here's the acid, here's the base. The acid is on our reactant side. And the base is on our product side. Okay. So which way, if my equilibrium says that my acid is 1 and my base is 10, which way is my arrow favoring? is favoring the product. So we're pushing more in this direction. So we have a bigger arrow in that direction, right? So if I have 10 over 2, I mean, which one is being favored now? So in that case, it would be the reactant, right? Because then that would give me a positive number. The log of 10 over 2 is going to give me a positive number. The log over 1 over 10 is going to give me a negative number, right? Okay. So when we look at this equation, I mean, we look at this graph. Yeah, you can already base it off of that, right? But often what happens is that you'll have an equation that's kind of like this. They'll show you the data like this. And so you need to be able to interpret what that data says. So this data tells me that which form is being favored. Okay, does that make sense? So if it's a negative, okay, so that means, okay, we're lacking in this area. The acidic form, this form here, acidic form, it's really weird. The acidic form, they should use the same colors, right? Is going to be less than the basic form, which is weird. So that means that okay. Acidic form, not right. This one also has to be fixed. Oh, pK. So here's the pH. And then, so this is our pH, and this tells us how things compare relative to our, okay. Okay, so is a compound neutral or charged? Okay, so when we talk about neutrality of the compound itself, we can also use the equation to help us figure that out as well, right? So this is just these are our equations. So in this case, this guy has a negative charge, the basic form. This guy has a neutral charge. This guy has a charge event. So negative charge, negative charge. And then this guy has a positive charge. And this whole side has a positive charge, okay? So it says in the carboxylic acid is neutral in its acidic form. So that basically means that when you're an acid, you have the hydrogen attached to this oxygen, right? Giving you a total neutral charge. Hence, carboxylic acid in that form. Alcohols is neutral in its acidic form. Again, you have that hydrogen attached to the oxygen in that form, where the amine in its acidic form has an additional H plus, right? You guys get that because the amine alone is a base. So we need it to have that H plus to have the charge. Okay. So, and then other side, we know that means that it's charged in the basic form, it has a negative charge. Okay. Alcohol has a negative charge in its basic form. And then the amine is neutral charge in its basic form. Okay, so when it's a base, it's negative. The easiest way to remember this is, so ammonia. Ammonia is a base and it has a neutral charge, where the ammonium ion is an acid, right? And it has a charge, right? And then that's the same thing with water here, like H2O. So H2O has a neutral charge, but H3O plus, right? That's charged. Okay. Questions? Concerns? Okay. Now, this here, so we have water, diethyl ether. It forms two separate layers. So diethyl ether is less dense than water. So diethyl ether is going to be on top of water. Right? So this is going to be, it's going to be pretty interesting because diethyl ether, so neutral compounds are going to be able to be dissolved in diethyl ether, where charged compounds are going to be able to be dissolved in water, right? So things that are neutral, we could sit there and collect in this layer. So what we would do is we get a layer of diethyl ether and we'll get water. And then what we'll do is just mix it all up. And then what happens, all the things that are neutral are going to go with the diethyl ether. And then the stuff that is charged is going to go with water. And so it allows us to do separation. So we can sit there and play with the fact that water likes charged stuff, right? And diethyl ether likes neutral stuff. So we can use that to do separations, right? And you guys are going to be doing that. You're going to be doing quite a bit of that, okay? We also talk about buffered solutions. Buffered solutions are solutions that contains both an acid and its conjugate base. And so it allows it, since it has both forms that are present there, it allows it to sit there and maintain a range, a pH range, okay? So you can add quite a bit without adjusting the pH, okay? Yes. Yes. So basically it allows you to keep your pH relatively constant, right? So you can maintain a pH of a certain, so you could add stuff to this, you know, and it won't change your pH too much if it's in a buffered solution. Okay. And you guys will be playing with that too. These are some examples. So if we have, so acetic acid and sodium acetate. So that's an example of a buffered solution. You have the acetic acid, and then you have the base, the acetate, okay, in the same solution. It allows it to be buffered. Okay, so formic acid and sodium formate. Again, another buffered solution. This one is methyl ammonium chloride and then methyl amide. So here's methyl ammonium chloride and then methyl amide. So again, another buffered solution. Okay. Okay, so remember when we were talking about that acceptor of electron pairs, right? Is it an electron donor or an electron acceptor? Okay, so those are Lewis bases. So Lewis acid and bases. So a Lewis acid accepts a shared, a species that accepts a share in electron pairs, where a Lewis base is a donor, a share of electron pair. So in other words, the base donates the electrons. So that was exactly what I was showing you was going on with that arrow earlier, right? So Bronsted is another way of defining acids and bases. So all Bronsted acids are going to be Lewis acids. All Bronsted bases are going to be Lewis bases. So there are two guys that came up with the same idea of the concept of using the electrons as the way of defining the acid. So if it's accepting electrons, is it an acid or is it a base?
Acid.
Acid, that's right. So acids accept, you know, bases donate. Okay. Okay, here. Oh, I hate it. I was going to tell you, ask you, which one is the acid, which one is the base? Okay, so the aluminum chloride is going to be our acid because it's going to be accepting the electrons. So then the dimethyl ether is going to be our base. Okay. Here, which one is the acid? Same concept, right? Next time I won't put the arrows and everything there up, so. Okay. Let's see. Okay, so we've talked about a lot of times when we define our acids, we define them as proton donors, right? So that's how the Arrhenius acid is defined, as a proton donor. And then where the Lewis acid is it's the opposite. What is it? It's an acceptor of what? Of electron. So it's electron acceptors. So then people say non-proton donating acids, so electron acceptors. So all bases are Lewis bases because they have pairs of electrons that they can share. Okay. Okay, that's it. Okay, we finished 5 minutes early. Woo, party.